So I'll post exam 2 after class. Well, right, not after immediately after class, but tonight. And it is due Thursday by 11:59 p.m. So hopefully you guys will have questions, or if you don't, that's fine too. But if you have questions, hopefully you ask, and it'll be fun. Speaking of questions, does anybody have a question they want to ask me about anything? The class, any problems? We did most of the homework last Thursday, I believe. So that's encouraging for us. Does anybody have a question or a comment?
I have a quick question.
Yes, I would like to hear it. What is it?
So on the Pearson homework,
Yes.
I've run into Euler's method.
Yeah, right. We didn't talk about this yet. So, I'm going in a slightly different order than the book. So we will, and I don't even know if we'll cover Euler's method. That is a method for solving differential equations, what we call numerically. If you have a particular problem about that, you can ignore that right now. If you're interested in learning about it, Paul, I'd be happy to do it with you. But we're not going to talk about that until we might get to it. It just depends on how much time we have.
Okay, sounds good.
Yeah. Yeah, that's a topic sometimes we get to, sometimes we don't. In the summer, it's hard because of the limited amount of time we have. But that's not always covered in Calc 2 anyhow. Usually that's reserved for a class in differential equations. Okay, does anybody else have a question?
I had a question about 7E on the homework.
7B?
E.
Let me pull it up. All right, give me 1 second. And this is homework 5?
Yeah.
7E. Okay. Do you have a particular question, or you want me to talk about it?
So will we just do that the same way you showed us, or at least a similar way you showed us how to do question 8 last week, or?
No. So E you can actually compute. So the difference between E and 8 is in 8 there's nothing you can do. There's no antiderivative so that you can use the fundamental theorem of calculus. However, on E, let's look at it. On E, you can get somewhere. So let's look at E. So
is it parts?
It's not parts. Well, actually, I don't know. I don't. Maybe parts would work. No, it won't. Parts will not work.
Okay.
Maybe it will. But the quick way to do that, or not the quick way, the way that I would do it, I shouldn't say it's quick, but the way that I would do it is do substitution. So let's suppose we want to integrate from 0 to t, right? Because we're going to take this limit, right? And so the way I would tell you to think about this is set u equal to x squared. And then your du is 2x dx. So what does this integral become? Well, the x dx is du times a half. So this becomes 1/2 e to the negative u du. So if you do a substitution, you get this integral. Now your bounds, let's look at your bounds. Your bounds, if x is 0, then u is still 0. But if x is t, then your upper bound becomes t squared. So does that make sense?
Yeah.
Yeah, now this is an integral that is identical to the one we did in class. I think we did e to the negative x in class. And so this thing you can integrate. This becomes negative 1/2 e to the negative u from 0 to t squared. And then you plug in t squared. So you get negative 1/2. And then you get e to the negative t squared. And then you get minus a minus, so it comes plus 1/2 e to the 0. So if you simplify this, this is just e to the negative 1/2 e to the negative t squared plus 1/2. Now, if you take the limit, when you take the limit, this guy goes to 0. So in the limit, you end up just getting 1/2. Is that clear? Does that make sense? I'm not. Yeah. Okay. So yeah, so that's a good question though, because E and problem 8 almost look similar, but they're not. And that extra x inside of there allows us to use substitution. Now, if you look at C, C looks similar as well. C is going to be done by parts. And then, you know, the other ones are just straightforward. Does that make sense? Anybody else have a question about this? That's a good question. It's often worthwhile comparing and contrasting things that look similar, but there's just a subtle difference. And that's what we have here. Any other questions on the homework? All right, so if there's no homework question, what we want to do is we want to talk about an application. Well, not an application, but it's because it's not an application. It's, you know, oftentimes students will say, okay, what good is integration? And that's a great question to ask. You know, in calculus, we spend all this time talking about integrals, and then if you're inquisitive human being, you're like, well, what good is it? Okay, sure, you told me I can compute areas and volumes and forces and other stuff, but what about like practical problems? And really integration has many practical uses, and one of them is, hold on a second. My house is going to collapse. The kids are fighting. It's wild. I didn't think a 5 and a 2-year-old can be badass, but they're out there wilding out. All right, anyhow. So our next topic is, and Paul, this is sort of what you were hinting on, but we're going to, we're going to talk about it in a slightly different order than the book does, just because I feel like it's more natural this way. So our next topic is what I would call an introduction to what we call differential equations. So this is a brief intro to the language of nature. Also known as differential equations. So if you're an engineering student or a math major or some other majors, you often take classes in differential equations, and there's just lots and lots to learn, and there's lots and lots of unknown things still that many humans get paid to study for a living. What we're going to give you today is a brief sort of intro to them. Why do I call it the language of nature? Well, you're very familiar with a differential equation already if you've ever taken physics. Because Newton's second law is in fact a differential equation in a general setting. You guys will remember force equals mass times acceleration. And as you will also recall, acceleration is the second derivative of your displacement. So keep that in mind when we're doing what we're doing. So let me introduce it this way. So what is a differential equation? So a differential equation which we're going to denote dE, is an equation where the unknown is a function right, so the unknown is a function, and the equation also includes the unknown function's derivative. So what does that mean? Well, the best thing to do is just look at some examples. And I guess I should say it this way. It could also include derivatives, if possible, maybe a second derivative, a third derivative. So what do they look like? So they might look something like this: dy dx plus 4y equals 6x squared. So let me explain to you what I mean. So here the unknown is y. And then what's the independent variable? Oh my God, these kids. I'm gonna kill my kids. I shouldn't say that, that would be mean. All right, so the unknown function is y, the independent variable is x. So your job is to find a function y that satisfies that equation. Let's look at another one. How about we have something like, we'll write it slightly different, x prime of t plus 3tx equals the sine of t. So now this is scary looking, but we can still tell you what, by context, here the unknown function is x, and the independent variable is t. And we can even do another one. Let's do one more. How about we take something like y double prime equals negative y. Now, I have not been explicit here what the independent variable is, so you can choose any letter you want, t, x, I don't care what you would choose. But here, the last thing we'll notice is the unknown function is y. So what's the goal of solving a differential equation? Well, the goal is to find a function that makes the statement true. What makes these things true? And the study of differential equations is very systematic, sort of like the way you studied algebraic equations in algebra class. You first study the simplest types, and then you classified them. You would start with linear equations, then you studied quadratic equations, and then you studied polynomial equations, and then you studied rational and radical, and then you graduated to trig equations. So you sort of build up the level of difficulty. And that is very much the same thing that's done when we study differential equations, although that would be left for a class. So what we're going to do is just give you a brief intro to these things. So there's lots of sort of analogous things to what you would have learned in an algebra class. So some useful terms. So the order of the equation is the highest order derivative that appears. So in the previous 3 examples that I gave you, the first one is order 1, and then the last one is order 2 because there's a second derivative that pops up. So you should be familiar with that. The next is a first order linear equation. And this is a very common type to be able to recognize because they can be solved rather systematically. So this is an equation that can be written as, typically we write it like this: y prime plus some function of y. So let's say we'll call it p of x, excuse me, some function of x times the unknown y plus some other, or excuse me, equals, let's write it in the standard way the book does, equals some other given function q. So let me put some important annotation here. So y is unknown, and then p and q are given. Okay, so that's scary language, but it's nice to be, you want to be able to learn how to write equations. You know, it's just like an algebraic equation. You can move things around as long as you follow the rules. And if you can write an equation in this form, if you can make it look like this, then it's called a first order linear equation. We'll show you how to solve those guys in a little bit. Does anybody have a question? Okay, so, and this is going to look very scary, but you guys, at some point we have to grow up. So, in general, a first order equation has the form y prime of x equals, and in general, it just could be some expression on the right-hand side. We don't know what it is. It's going to be some sort of conglomerate of sines or cosines or polynomials or anything. And so what we do is we write it like this. So this is what a first order equation looks like. And for those of you who get scared by the right-hand side, all this means that the right-hand side is some expression in t, and y. Or excuse me, not t. I shouldn't write t. That I'm using too many letters here. This should be an x. So that's just a generic differential equation. And so in most practical problems, we have what's called an initial condition. And what does that mean? This initial condition might mean that we know at least one value of the unknown function. We know at some point A, it spits out some value B. Does anybody have a question? So, you know, if we put these things in into our current world, you know, all the talk about the COVID and all the, you know, all these, the talk you hear about modeling and trying to figure out how disease spreads. One of the ways that scientists study infectious disease and its spread is through differential equations. You can Google that and you'll learn all kinds of interesting things. So differential equations are everywhere, and in many ways they're the language of nature. And this comes from Newton's second law, mostly, that force equals mass times acceleration. So, you know, if you're looking for a reason that this could be interesting to you, then there you go, other than just the scary abstract math that you see on the board. So one last term before we start doing some actual examples is, if an equation is paired with an initial condition, we call the pair an initial value problem. Which is typically denoted IVP. So that this would come like y prime equals some expression in, say, x comma y, and then it comes as a pair that when you plug in A, it spits out some other number B. So what's the big question out there? How do we solve them? By the way, Paul, it reminds me of your question about Euler's scheme. If any of you paid attention to, you know, a few years ago, there was the movie about the moon landing and the NASA engineers called Hidden Figures. And one of the key points of that movie, which is sort of Hollywood dramatized, is when the main character figures out how to re-enter, she's talking about this calculation and get the astronauts back into Earth without dying. And one of the key things is how they use Euler's scheme to solve the differential equation. So you can read all about that if you want on the internet. Maybe I'll get some links if you're curious about that stuff. But really, if I had to explain to a group of people why math is useful, it would be because differential equations. And it's not my only belief that that's why math is useful. But if you got to convince people why they should study mathematics and why we want smart people to do it, it's because most of the observable world is written in the language of differential equations. And so if you want to explain things like how drugs are infused and how free fall happens and how do we launch astronauts into space and how do we understand how we could model population growth in a river or a lake, or how do we model money in an investment? How do we study how tumors grow? How do we study infectious disease? All these things are done, and many more things are done through the language of differential equations. Okay, so does anybody have a question? Comment? Oh, someone's chatting. Did I miss this from earlier? That's a good one, Paul. That's very good. Very, very well done, Paul. It's like my hypotenuse joke. Okay, so there's some good news and the bad news is bad news. Most differential equations can't be solved by hand. What's the good news? Well, there's two good newses, two good pieces. Many important ones can. And the second part of the good news is what we can't do, computers can. And it's not that we can't do it, it's just that we're humans and it would take us a lifetime to do something that a computer can do in a second. And so if I can tag back on to, Paul, your initial question about this Euler's method, if I asked you to do Euler's method by hand to solve an equation, it would take you quite some time. But now, thanks to technology, a computer, and it's not hard for you to do it, you can even write your own code to solve these equations very rapidly. Which reminds me, Michelle, you asked about how to program numerical integration. I got to send you that. See, my brain. Okay, so in this class, though, we will study two types. That's it. This kid's out of control with his poor spelling. Of course, you guys know that. Many of you had me in class before. So in this class, we study two types. That's it. So if you want to learn more, look how I use that word. That's so great. Well, take higher math courses. Some of you will be forced to do this because of your degree. Others won't. Okay. Does anybody have a question? And by the way, there's tons. I mean, if you were at a big university, they often have a few differential equation courses, even for undergraduates, that you could take. You'd have an intro one, then you can have some upper level ones. There's lots that you can do with these kinds of things. Okay, so let's learn through example. So let's look at sort of a pretty basic equation. Let's solve this. Let's solve y prime equals 3t squared over y. So at first look, if you get too cute, you might say, well, okay, I have the unknown is y. Why don't I just integrate both sides, because that'll kill the derivative, and then I'll know what y is. And that might work in some simple equations, but it isn't going to work here, because on the right-hand side, y pops up. And since y pops up on the right-hand side, I can't just integrate both sides, because I don't know what y is. How the heck can I integrate something if I don't know what it is? So what I have to do is I have to be a little more creative. So one thing I might note is you know what? I see something here that I can take advantage of. Now, you might not see this because you're babies in Calc 2, and at that age, you guys, much like myself, all we're worried about is how do we do these problems? How do we do them? We don't really ever want to think about what's happening. We just want to learn procedures. And again, that's not our fault. That's been our math education our whole lives. But if we once in a while take a moment to think about what we're doing, we actually learn that there's patterns and themes that we can be taking advantage of. And this requires lots of practice, of course, but sometimes all the suffering in practice makes it worthwhile when you make this discovery. So what I'd like to do is I would like to think about how I might use my knowledge of calculus. So here's an idea. So let's rewrite, and I'm going to rewrite this as y times y prime equals 3t squared. And then I'm going to write it even more descriptive. I'm going to write it as y times dy dt equals 3t squared. Now, what typically happens at this level is someone who's taking Calc 2 doesn't see that the problem is solved because you just don't know enough yet, and that's okay. But for someone who has a good understanding of calculus and integration, what they recognize is that the left-hand side is something that can disappear. So what I'm going to do is, how do I make it disappear? To make it disappear, I say, let's integrate. With respect to t. So if I do that, let's look at what we get. So if we do that, on the left-hand side, I have the integral of y times dy dt. dt must equal 3t squared dt. Now the integral on the right-hand side is very simple. You integrate it, it's 1/3, times 3t cubed plus some constant. That's not a difficult integral. But the integral on the left-hand side, well, what we look at that it looks very confusing. It looks like a bunch of symbols. But if we recall how integration by substitution works, if we recall the change of variable, then the left-hand side is nothing more than the integral of y dy. Now, you're going to say, huh? How does that work? Well, if you're having trouble seeing it, think about using a different letter. Maybe that'll make it clear. What if you set, and this is just, if you're still unsure about this, let's come over here and let's say you're going to set y equal to u. Well, then what's dy? Well, dy is just what? du or maybe that's actually more confusing. Maybe let me erase it. Let me I'll get you to think of it another way. What is, so go back to, I need my pen back. Let's change t. So let's go from t to a new variable. So let's say u for the sake of an argument. Okay, then what's dt du? Well, dt du is just 1. So that means dt equals du, correct? So what does that leave for us on the left-hand side? Well, if we started with y of t, then that's going to become y of u. And then what's dy dt? Well, all that becomes is what? Well, that's just dy if you match it with the dt. So again, it's sort of difficult. I think part of it, what makes it difficult for us as sort of students in Calc 2 is we're just not that comfortable with things like change of variables. We're not that comfortable with the chain rule. And hence, it's difficult for us to see how this is behaving. Because what happens is often, I shouldn't say often, what we can do is if we you know, in a cheating type of way, what you can often think about is that, and this is what we do just to save time, is we literally just think about this and this canceling, even though we know that's not true, but they do cancel out because of integration by substitution. Does anybody have a question? Because the key thing to note is that what made the integral up top impossible, not impossible, but was confusing, it was that the variable was t and y is unknown. But because of this change of variable, the variable becomes y, and so we can now integrate. Because, and I don't know if you're following, I hope that you will ask questions if you're stuck, because what this says is this is just now 1/2 y squared equals t cubed, and then we have our arbitrary constant floating around, so we just put our plus c there. And now we can solve for y. Because y is, or y squared at least, is 2t cubed plus c. Or y, taking square roots, can be plus or minus the square root of this expression. Does anybody have a question? Comments? So there's a couple observations that we should talk about. The first one, we actually have infinitely many solutions. One for each c. You pick your favorite value of c. As long as that square root's defined, we have a solution. So let's be more, was it 2 or no, 3? No, 2. T cubed plus c is defined. And the second remark is that our strategy should apply to many equations. So if you look at our strategy, how we did it, you would imagine that perhaps if we can isolate and get all the y's on one side and all the t's on the other side, that all we can do is integrate and voila. So So we call an equation separable if we can write the equation in the form y prime equals some function of y, which I'll call g, times some function of the independent variable, which we'll call h. So in general, we don't necessarily able to do this, but if we can do it, then things work in our favor. So let's emphasize that. So we can solve separable equations by separating the variables and integrating. So if you can be separated, then this strategy works, provided we can integrate the functions. Let's do another example. Or more. So let's do one example. So let's take dy dx equals e to the negative y times the sine of x. How do we solve this? Well, we note that on the right-hand side, I can separate my variables into two distinct functions. So what I do is I'm going to rewrite this as e to the y dy. I put all my y's on one side and all my x's on the other side. So I separated the variables, and now I can integrate. And when I integrate, I get e to the y equals, what's the integral of sine? It's negative the cosine plus c, and then I can take my log and I get y. My solution, y equals the log of c minus the cosine of x. Does anybody have a question about this?
Excuse me, Professor.
Yes,
Why do we go from e to a negative y to e to a positive y?
because I took it to the other side. So if I divide by it, it becomes what? So if I take you to the other side, so if I had if that was 5 sine, what would it be on if I took it to the other side? It'd be 1/5, right?
Oh, right. Okay.
Okay, so the negative, does that make sense?
That makes sense. Yeah, I got it.
I have a quick, I guess, mathematical semantic question.
Yes.
So if you had sine of x and you wanted to integrate it, your term would be the integral of sine x dx.
Okay.
So when you have the expression sine x dx already and then you integrate it, that's still just the integral of sine x dx?
Right, so that's what the point I was trying to make with the original example is we're sort of cheating with our notation. so we're again, so if you got to go back to the previous page, really what we should be writing here, and that's the kind of point I was trying to make, and maybe I did a poor job of making it. What we should be writing here is the integral on the left should be dx, and the integral on the right should be dx. But what I'm telling you is because of the theory, it works. So you can just sort of write it this way, even though it's sort of illegal. Does that make, I don't know if that makes sense. So I think your question is, how do you write dx here? It doesn't make any sense. And I agree with you. What I should be writing is I shouldn't, if anything, what I should have is I should have this here and here. Does that make sense? Now it's not wrong. But what I'm just trying to get you to do, and it's poor notation, you're right, is I'm trying to get you guys to understand that we can quote unquote separate the variables. Get everything that's an x on one side and everything that's a y on the other side. Do you understand what I'm saying?
Yeah, I think so.
Yeah, again, it's, you know, so there's two ways to think about this type of problem. You can either look at the original example and try to understand what's really happening, or you can do this shortcut and just, you know, ignore the correct sort of language. And that's up to you how you'd like to do it. What I wrote here is not wrong. It's just abusing notation is a better way of thinking about it. Do you follow what I'm saying? Okay. Let's do another one. Maybe this will help clarify your qualms, Paul. Or does that even make sense? I don't think so. Let's look at another one. Let's say dy dt equals, how about y over 1 plus t squared, like this. Well, okay, so what I'm going to recognize is that I can separate my variables. I get 1 over y dy is the same as 1 over 1 plus t squared dt. Now I'm going to integrate. And so on the left-hand side, I'm left with this log of y. On the right-hand side, this becomes the arctan of t. And then I have my arbitrary constant. And so now, how do I solve this for y? I have to take the x, e to both sides. And so you're left with y equals e to the arctan of t plus c. But that looks kind of silly. So what we usually do is we'll write this as y equals some number, we'll call it a, e to the arctan of t. So again, you'll notice that we're sort of abusing notation, but it's not illegal in the sense that it's just poor, it's poor notation, but it's theoretically sound. It's mathematically correct because what you're really doing in the left-hand integral is you're using a change of variables. You're just not writing it because it's redundant. That's exactly right. It's sort of cheating, Paul. You know, oftentimes, that's one of the poor habits that we often do is we abuse notation, and I think it makes it harder for students to learn, and that's unfortunate, but you have to still show, you guys have to be aware of what you're going to see, not just from me, but from maybe YouTube videos and stuff like that. I don't know why. Okay. Well, hold on one second. Give me 30. No, hi, James. The test is coming today. It'll be given after class, and it's due Thursday. Is that clear? Hopefully. Yep. All right. Does anybody have a question about this, by the way, these things, these two examples? Cool. All right. So let's pick up where we're going. All right. So, so what are we going to do next? So the next type of equation we will solve is we're going to circle all the way back to the most common, I shouldn't say the most common, but one we can solve that has endless applications. Are the first order linear equations. So these are the guys of the form y prime plus p of, say, x, y equals q of x. So what we typically do is let's not study it in the general case yet. We could if we wanted, but let's go much simpler, and then maybe we can recognize something that's happening, and then we could take advantage of it and see if it works in a more difficult situation. So let's start with p of x and q of x being constant. They don't depend on the variable. So let's look at an example. So let's start with something like y prime plus, how about 3y equals 11. So I'm going to pick two numbers, and I'm going to pick them so that they don't have any common factors. Or what I'm trying to see is is there some sort of something I can pick up and learn from this. Okay, so one of the things I want you to sort of ponder is the left-hand side. Because once again, depending on how much we recall or how much we know and how much we like to investigate and think, the left-hand side might stand out to us as something. And it's not something we learn in Calc 2, although we use it in Calc 2 all the time. But if we look at the left-hand side, we see y prime and we also see y. And so for someone like myself who looks at and does math for a living, what I recognize is something on the left-hand side that looks Like it might be the product rule hidden in there somewhere. And the reason that that intrigues me is because if that's the product rule written in there, if the left-hand side is a product rule, and I can write it as the derivative of something, and then the right-hand side is just a number, well, then I can just differentiate, or excuse me, integrate to kill the derivative. So the left-hand side intrigues me because I think I can get it to look like something that I can undo. Now the question is, how do I do that? And so one thing I could do is I can do trial and error. I can say, well, let's multiply both sides by something. So here's my goal. Multiply both sides by something that lets me rewrite the left-hand side as a derivative. So now I'm going to save us some time. But here, if you think about it, you'll say, oh, that makes sense. Here, the magic choice is e to the 3x. So I'm going to multiply both sides by e to the 3x. So I have y prime e to the 3x plus, if I look at, and if I rewrite this, instead of me writing it in the order I did on the previous page, I'm going to write it as y times 3e to the 3x. And then on the left-hand side, excuse me, on the right-hand side, I have 11e to the 3x. And so if you think about that, now I have the product rule here. I have y prime times something plus y times the derivative of that something. So this really can collapse to y times e to the 3x, quantity prime, equals 11e to the 3x. And now I can just take the derivative, or excuse me, the integral of both sides. So I have y times e to the 3x has to be the integral of 11e to the 3x. And so when I integrate the right-hand side, I get 11/3 e to the 3x plus c. And now I can get y. All I have to do is divide both sides by e to the 3x. So if I do that, if I just do the appropriate quote-unquote algebra, we get y equals 11/3 plus c e to the negative 3x. So you might want to, I'll pick on you, Thomas, because you asked that before. Think about why is it written like this? Oh, I forgot I wrote that wrong. This is c times e to the negative 3x. Any comments?
Just out of curiosity,
Yes.
why at the very beginning, why couldn't you just integrate y prime plus 3y equals 11?
So on the okay, so why couldn't I do that? Well, you don't know what y is. How are you going to integrate y? You could clearly integrate the first piece, y prime, that would just give you y.
Right.
But the 3y you can't integrate because then you're going to be stuck with the integral of y. There's no way of knowing what that is without knowing what y is. So the ingenious trick is to rewrite it so you don't have to do that.
You wouldn't end up with y plus 3 halves y squared
No,
equals.
no, because you would remember you're integrating with respect to the variable. You got to be careful. Remember, so that y prime, that represents dy dx or dy dt. So if you look at the next page, what I'm doing, the variable is x. Y is the function. So you have to, you see, that's a good question, because one of the biggest difficulties for students at this level is us understanding that there's an independent and a dependent variable. And we didn't do ourselves any favor when we do those separable equations, because we're sort of cheating, like you brought up. I mean, we're not cheating, but it seems like we are. So now that confuses you, because, right, you're going to say, why don't I just integrate this and get y plus 3 halves y squared equals, well, that's not how it works. If you're going to integrate the expression, you have to integrate all the pieces by the same variable. Remember, integration, like differentiation, is with respect to a variable. So you have to be very careful with that. Does that clarify things a little bit for you? Maybe?
Yeah. And then I was just wondering, as an application for this,
Yeah.
when you end up with your final answer, you could have like infinite outcomes, since the constant could be.
I mean, there's infinitely many solutions here. It depends on what you want to pick for C. Now, if we're doing practical examples, then you're going to have limited things, and then you're also going to have, like, if you're talking about, say, drug dosing, or you're talking about chemical reactions, or you're talking about investments growing, where you're going to have some realistic initial condition, like the amount of our fund is $1,000 on day 0, or the amount of medicine in your body at time t is blah. You understand what I'm saying? So we're just solving these in a general sense, but we could ask you, I could say to you, what's the specific solution that passes through, y of 0 equals 5, and then you'd have to determine C that makes that true. Does that make any sense?
Yeah, so in a practical scenario, you would most likely be solving for C.
That's exactly right. Not solving for C, you'd be determining the C that goes with your practical problem.
Okay.
Right. So we'll give you some problems to work on that. It's just, I want to first make sure we know how to solve the equations first. Does that make sense?
Yep.
Okay. All right, so here's the cool fact. This quote-unquote trick works. And I hate to use the word magic here, because it's really not magic. If I look at this, I mean, even though I said it's a magic choice, it's an educated guess of a choice. I mean, look back at the original equation. If I'm looking for a function that would satisfy this, I have to guess that the exponential function is going to be involved. Because look at this, it's the only function who, when you differentiate it, it stays, think about a polynomial. If you differentiate a polynomial, it loses a degree, right? If you differentiate x squared, it becomes power 1. Well, there's no way a polynomial would satisfy this, because we're asking you to add the derivative to 3 of the original function and get a number. There's no way that's going to work with a polynomial. So me using this, what I call the magic choice, it's very much an educated guess. Now, there's always some trial and error involved. But it turns out this trick works in general. So if you want to solve y prime plus px, excuse me. If you want to solve y prime plus pxy equals qx, you multiply both sides by, now this is going to look scary, you're going to multiply it by e to the integral of p. Yikes. Now, I'll spare you the ugly details, but just to give you the bullet points, and if you want to really gauge how well you understand this, fill in the details yourself. So when you do this, what you obtain on the left-hand side is you obtain y times e to this integral of px, whatever it is, prime, equals e to the integral of px times qx. And then, of course, you can now integrate both sides. You get y, and I'll just give you the formula. Y of x equals, it equals 1 divided by e to the integral of px. Now, this is going to look scary. Don't be mistaken. Times the integral of this qx dx. Now, do not try to memorize this. That's not the key. The key is to do problems. Because this is ugly. You don't want to, this looks like a hot mess. There's integrals everywhere. It looks very overwhelming. But it does work every single time. All right, so let's do an example of one that's not just numbers to show you what we mean by this. Does anybody have a question before I do anything? Going once, going twice. All right, so let's do one. We'll go slowly. So let's say we have dy dx plus 3x squared it's going to be an ugly one, but such is life. 3x squared y equals 6x squared. So here's how I would encourage you to think about it. So e to the integral of px here is e to the integral of 3x squared dx, which becomes e to the 3x cubed over 3. So this just becomes e to the x cubed. So let's multiply both sides and recognize the product rule. So when you do that, the left-hand side becomes y e to the x cubed prime equals 6x squared e to the x cubed. Now, if you don't believe me, just take the derivative and work it out, and you'll see that that's what we started with, I promise you. But the only way you're going to learn is if you do that yourself. Okay, so if you do that, then the next thing you do is you integrate. And on the left-hand side, we have y of x times e to the x cubed is equal to this integral. Now it looks like an ugly integral, but it's actually a very basic substitution one. So let me tell you that if you choose u to be x cubed, then your du is 3x squared dx. So this integral right here, when you take 3x squared, you're left with 2. The integral of u, excuse me, not u. The integral of e to the u. Du, which of course is just 2e to the u plus c. And then if you plug that back in, you're left with 2e to the x cubed plus c. So the only thing that's left for me to do is for me to now divide through by this e to the x cubed that's on the left-hand side. So we don't have to go to another page. Let's stick it up here. So hopefully you guys. So what we found, if we found that y of x times e to the x cubed, I'm running out of space. What we found is y of x e to the x cubed is equal to 2e to the x cubed plus c. And then we can divide through, and we're left with y of x. Our solution is 2 plus ce to the negative x cubed, if I get cute with my exponents. So this is for the amateurs like you guys, this is a difficult calculation. So it's going to take you some time if you go through the pieces, but I would highly encourage that you do. Any questions? So this is challenging. Hopefully you'll work through it. What we'd like to do right now, though, is I'd like to extend it similar to what was asked. So what we're going to do now is let's get the particular solution that satisfies, say, y of 0 equals 3. So if we look at our solution is 2 plus ce to the negative x cubed. So y of x equals 2 plus ce to the negative x cubed is what we call the general solution. because as we pointed out, it's really a family of solutions. So to satisfy y of 0 equals 3, what must we have? Well, you must have 2 plus c e to the 0 equals 3, which implies 2 plus c equals 3, which of course implies c equals 1. So the particular solution is y of x equals 2 plus e to the negative x cubed. Does anybody have a comment about this or a question? Going once, going twice. Okay, so I'll give you some practice problems and hopefully you'll ask questions about them. Any other questions before? I think it's a good time to quit. And then we'll give you your test in a little while and then you can work on that. And hopefully you have questions. You can ask me, email me, whatever. Does anybody have any comments, questions? All right, I thank you guys for joining. Please reach out if you have any questions or concerns, and I will talk to you soon. Don't forget, we're not going to have class Thursday unless you guys want to meet. I want you to use that time to work on this. So if you have questions, I'd be happy to meet with you if you want to get together. All right, everybody, thank you very much. Take care. I will talk to you, well, maybe I won't talk to you until next Tuesday. Be safe, guys. Take care.